That's at the bottom of the second page where optimization ends. Actually, let me look. Yeah, it's back there. All right. So we're gonna, if we talk a little bit of hyperbolic functions here, I mostly think I need to remind you these. All the derivatives were virtually the same as you already know, except for two. Derivative of hyperbolic sine was hyperbolic cosine, and the derivative of hyperbolic cosine was it positive or negative hyperbolic? It was one of the ones that changed. It stays positive. Yeah. It's one of the ones that has a change on it, the hyperbolic cosine, and then cosine's reciprocal secant is the other one that's changed from what we know as our normal derivative. So, hyperbolic tangent is still secant squared. Cotangent doesn't change. I'm leaving out my x's here. It's still negative cosecant squared. And the other one that changed, hyperbolic secant, becomes what? What would be the opposite of what? It's negative secant tangent, yes. And hyperbolic cosecant is still negative also. So, now, with the hyperbolics, I might ask you to do a derivative of one of them, since we did do derivatives of them. I could ask you a product quotient chain rule type problem, or I can ask you to integrate with the hyperbolic. Cosine and secant are the two that changed. Yep, do the exact same thing, you just write the x raised in there. That's a real skill you got there. Thank you. So I might ask you, okay, here's a lovely function, hyperbolic cosine squared of 3x to the fifth over hyperbolic secant of 4x times cotangent of 5x cubed. So that's weird. Alright. So, oh no, can you do a derivative? Nope. I'm just not going to turn around and look anymore.
You've done derivatives before? What is that?
Do we know now?
Yeah, the area between a line and a curve.
Function in the axis, curve in the axis, curve in the axis.
Nope. You're wrong. You're wrong.
Okay.
No one believes Andrea.
Alright, now, today, pre-calc just finished their assignment today on product quotient and chain rule, and they think that something like this is very difficult.
Yeah.
I think so. It's very difficult.
What rule do you start with?
Where quotient?
Dylan thinks quotient. Yes, it is a quotient rule without the sound effects. Oh, you bet. I think every day about how much I miss it.
That song, like, it helped me remember that, though. I mean, you
So,
got
there's low. Now, okay, the high is what I'm worried about. How do you do? Yes, because it's chain rule. So it's 2 hyperbolic cosine to the first of what? Thank you. Are you done with that? Yeah, because now you got to do the cosine, which would indeed be a positive hyperbolic sine of 3x to the fifth, and then times the derivative inside of that, which would be 15x to the fourth. Are we done with the quotient rule? So minus pi d low. Oh dear, I shouldn't have done this on the screen. It's going to make this way wide. Okay, so high is hyperbolic cosine squared. And then the derivative of the low means we get to do what?
Oh,
Product rule. So, do you need me to backtrack or not?
Low on the top?
So, here was low, d high, minus high, and now we're ready to do d low. So d low is going to be, yes, a product rule. Okay. Okay, so first d second, second d first. So we have a hyperbolic secant of 4x that's going to sit there. What's the derivative of the second? Yes, a negative hyperbolic cosecant squared of 5x cubed. Yep, then times 15x squared because you got to do the derivative inside. Okay, done with the product rule?
No.
Nope. That's first d second. Plus, second is our hyperbolic cotangent of 5x cubed, and I need the derivative of the first, which is now off my screen. First is secant of 4x, hyperbolic secant of 4x, so that's not too bad. What's the derivative of hyperbolic secant? Secant. Is she right? Positive or negative? Negative. It's the one that changed, yes. So it would be negative hyperbolic secant of 4x tangent of 4x times 4, the derivative inside. And then the part you almost forget. Both squared.
Hold on, go back. You need handwriting? What? Look at that.
Wow. That was really not worth it.
Alright. And it was a lovely hyperbolic derivative. Okay. So I may ask you to do one of those, probably not that long involved, but
That's not hard. It's just
kind of early, but yeah, not that bad. Okay, then we hit integration, 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 and get down to more integration. Because you will notice the integrations run from letter A to letter BB. I ran out of alphabet and had to start over. Oh yeah, and here's the other semester review. I did that with derivatives. I ran out of letters and had to start over. I could go hexadecimal. Okay, so things I am concerned about with just integrations. For the most part, you probably just need to practice on integration. However, there are a couple ones that we haven't, a couple integration rules we haven't done in a while. I'm going to make sure you remember. So, for example, if I said how do you integrate e to the x, what do you get? E to the x. And if I ask you to integrate 1 over x, you get natural log of x. I should be putting plus c's on these. And then the one I'm really worried about, what if it's a number to the x power, like 7 to the x or 50 to the x? Halfway there. Anybody remember the derivative of a number?
1 over a to the... What over the natural log of the number?
Yes. 1 over natural log of a. Times the exponential function, yes. Because if you will recall, its derivative was nearly the same thing, except you ended up with natural log of a times it. Integration, you end up with the natural log on the bottom. Derivatives, you end up with the natural log on the top. Okay, do I need to, well, it won't hurt us to have the list. How are we doing time-wise here? Okay. What's the integration, not derivative, duh. What's the integration of 1 over square root of 1 minus x squared? Ah, yes, inverse sign back there somewhere. X times square root of x squared minus 1. That's Romeo seeking Juliet. And then, of course, if we have no roof at all, we are doing inverse tangent because we're catching the rays. So all those in play. Now I'm not listing them. Do I need to list the normal trig functions, or we got the normal trig functions? Like if I say, what's the integration of a secant squared?
Tangent.
A tangent. What's the integration of a cosecant cotangent? A negative cosecant. All right. So those basic derivatives, of course, you still need to know as well. But those are kind of the specialty ones that we work with. Okay. At that point, a lot of these are going to be ordinary U substitutions. Actually, let me ask you about the very first two because they may prove to be the most difficult. How do you do 8A? 8A.
Oh, let me get there.
Nope, not U substitution.
You did that.
Let's just multiply it together and do the power rule. Yeah, oh wow, they can be that easy. That worries me a little because it's been a long time since you did something that easy. Sorry. Okay, same way, 8B can be done with just a little algebra at the beginning. What do you do on 8B?
Bring the Y up top.
You bring it up and you distribute it. Yes, bring it up, distribute it, and that's just another power rule. All it is. Okay, after that, they're intermixed. There's quite a few that are just U substitution, but I did then start mixing in a trig substitution shows up here, a partial fraction there. Okay, what in particular is going to make you think it might be a trig substitution?
Negative cosine or secant or something like that.
What makes you think it might be an inverse? A square root of something squared minus something squared, although sometimes it's just an inverse trig function.
Are we gonna have enough room to do this all in here?
If you don't write gigantic.
You read gigantic.
So far.
Okay, probably there's not room to do partial fractions on there.
I bet Jill could.
Okay, Jill can probably get them all on there, yes. But so I used to not even give space. I just gave you a sheet of paper and told them to work it on their own, and they just thought I had killed them because I was asking them to work it on their own paper. So instead here, I did put in space, but if I put in gigantic spaces for all of those integrations, those 28 integrations, this thing would be a book. So I did not do that. I don't know exactly what to say to you about integrations at this point. We have to graph. I was going to say that for next time. Well, when did you have to graph this semester?
You did.
I don't remember graphing.
The area and volume. You remember you had to graph it out because you had to be able to do the top function minus the bottom function, or the right function minus the left function.
Whoa.
Okay.
Let's just do that, you know?
You want me to do that now? Or you want
Yeah, I
me to
gotta
keep
get
going?
prepared to teach them on Tuesday.
So, I can keep, you want me to just keep, actually, if we're going to keep rolling, then I'm going to cut to 9 and ask you if you remember how to do 9. It's really easy.
Hold on.
No, I'm not. How do you do number 9? I'm asking you to do the derivative of an integration.
Holy cow,
What did you put? Okay.
oh, it just erased double D. They oh my lord.
The derivative and the integration cancel each other, but you do have to make one change.
You have to change it into Y's, X's.
Yeah, because you're integrating from 0 to x there, So therefore, if you actually work the problem out, you would do the integration, you would sub the x in, so you would get an answer with x's in it, and then when you took the derivative of it, you would get back to the original function, except there would still be x's in it. So all you have to do on those, if I'm asking you for the derivative of an integration, it just switches the variable out, because otherwise they cancel each other out. That's the beauty of it, they're opposite operations. That was the second part of the fundamental theorem of calculus, big name for the triple concept. That's all it's saying. Okay, number 10, formula. Anybody remember doing average value? Oops, I'm over. Hold on, sorry.